So thank you very much for the invitation. I'm very happy to be here this time as a speaker. So I would like to talk about face image quality assessment, which is a very popular topic these days in face recognition. So I have this structured as a sort of a tutorial talk. So also if you're not familiar with the field or the problems, how what we are trying to do and how this looks like. I will first provide an overview of two of our methods, or three of our methods that we developed for face image quality assessment, FaceQAN, DifFIQA, and FROQ. And finally, I'll highlight some of the open challenges. So if you want to do research in this area, so that part may also be of interest to you. So let's dive into the background and concepts. So before we start with face image quality assessment, it's probably a good idea to define what image quality assessment is, right? So if we are talking about general images, there's often the need to say something about the quality of the images that we have, right? That may be from the perspective of the sensor, right? So how if the sample or the image that we captured was good enough, or it may be from the perspective of let's say signal processing or computer vision application where we want to do something with the image, and of course therefore it needs to be of solid quality, right? So if you try to look up what image quality is, you can find very different definitions online and in the literature. For example, if we look from the perspective of acquisition, right? So what we capture when we image a scene, you can find a definition like that, which says it's the level of accuracy with which different imaging systems capture, process, store, compress, transmit, and display the signals that form an image, right? So we are interested, for example, in how good of a sample we have captured with some sensor, some imaging sensor. Then if you look more from a human perspective, right, when we look at an image, it could also be the weighted combination of all visually significant attributes of an image. And that could also be quality, right? And if you think from a third perspective, for example, if we are thinking about degradations, then image quality could also be a characteristic of an image that measures the perceived image degradation. So how blurry it is, how much noise does it have? Is it crisp? Is it sharp? Do I see the details, right? Things like that could all somehow be related to quality. And so in general, there's different aspects to quality: noise, blur, sharpness, contrast, color accuracy, distortions, and a lot of different things as well. So you can see some examples here on the bottom slide. At the bottom of the slide, we can probably all agree that the images on the left are of good quality, and as we go to the right, they get worse, right? But it's very difficult to assign a number to that, right? So is, for example, this image of a dog worse than the image of the elephant over there? So that's not completely clear. And we as humans, usually we like numbers, right? We like to have a numeric score for each image so that we can say, okay, this one has maybe a quality score of 20, and this one a quality score of 40 on a scale of 1 to 100, for example. And that gives you something more tangible, right? So to quantify the quality of an image. And if you look at, again, still sticking with the general images, the different types of image quality assessment methods that there are, we usually divide them in subjective and objective quality methods, quality estimation methods, where subjective would usually measure how we, right, perceive the quality of images. And for example, if I show you this one and ask you to grade it on a scale of 1 to 5, where 5 would be the best and 1 would be the worst, we would probably get a distribution with a score, let's say, in the higher ranks, right, closer to 5. And then if I show you this image, which is the colors are off and it's blurry, we will probably get lower scores, and this would be an estimate of how good the quality of this image is, right? And this process, if I ask you, right, to estimate the quality, is usually called mean opinion scoring. So we give people, humans, example images, and then ask them to score them on a scale of 1 to 5. And this would give you an impression of the quality. But of course, there's problems with that, right? We cannot do that on scale. So if you need to measure the quality of thousands of millions of images, this is not really scalable, right? So we can do a study based on that, but that's mostly what we can do with that. So there was another branch of these methods that was developed to automate, right, this process of this mean opinion scoring process. And these objective methods, which are computer-based methods, they try to approximate what humans do, right? So the idea would be that you maybe annotate some images with human scores, and then you can try to build a model that predicts those scores directly from data. And again, here you have different approaches, which, for example, the groups are full reference image, reduced reference, or no reference images. And what this means is, for example, if we talk about full reference images, this is usually related to some sort of degradation or restoration process. For example, we would have a reference, so we know this is the standard, this is what we want to have. And then we have maybe some degraded images because of compression, or some blur, or some noise. And now full reference methods would measure the similarity or somehow the quality with respect to the original. And you know, the simplest idea that comes to mind on how to do that is to compute the mean square error, right? So that would give you a distance, sort of a distance, how far away this blurry or this noisy image is from the original. But you can see what happens if we have some naive methods like mean square error, which is not a good quality measure per se. The blurry image would get a score of 310, but also the restored image, which probably most of you would say is of good quality, would get a score of 306. So basically all the scores are very similar because per pixel measurements are not the best approach to quality estimation. So we need something better. And already better measures are some perceptual similarity or structure similarity and things that you probably are aware of, right? And then what is probably the most relevant is no reference quality estimation, right? Here you don't have a reference image or ground truth to tell you this is what we want to have, right? You just have an image and you need to produce a quality score. And this is also what we are interested usually in face image quality assessment. So if we move from general image quality assessment to face image quality assessment, it's basically the same thing, right? So we want to estimate the quality, but this time for face images. And here we have a lot of specifics how we want to do that and why. So it has a lot of use cases. For example, if you think about what's really active and popular today, it's generative models, it's synthetic data generation. And we want to be able to tell if the images, for example, in this case, facial images that we synthesize with some Gen AI approach is of high quality. And that would usually mean that it's useful for some other downstream task in computer vision. Or if you do research, for example, on super resolution or face restoration or something like that, then you are interested usually in how good your restoration or super resolved image is, right? You can do that in, let's say, full reference manner if you have the ground truth. But if you have real world low resolution or low quality images, you don't have the ground truth, right? And here again, you want to be able to tell, is what I have restored of good quality? And this is not as simple as just computing the signal to noise ratio or the mean square error or something like that. It can be much more elaborate, right? But the main application where face image quality assessment becomes relevant is actually face recognition. So consider this mobile face recognition scenario that's on this slide. So if you think about mobile phones and acquisitions conditions, they're usually not constrained. That means you can be outside, there can be very off illumination, maybe the focus is not the best, it can be dark, right? All of those factors, they impact what kind of quality image you acquire. And so sometimes it can happen that this image that should go into a face recognition model to produce the template and then later on the recognition result is not of good quality, right? So you can have a bad quality image. And when you can estimate if you have a bad quality image, right, then this typically does two things. First, overall, it decreases performance of a face recognition model. And you can see this also from another perspective, that what you get in terms of decision or let's say comparison score is unreliable, right? If I match a bad quality image to a gallery that I have somewhere and the bad quality image is really bad, then I will get some decision, right? But it will not be reliable. So here's where face image quality comes into play. So we can estimate what the quality of this image is. And if it's too low, we can simply ask the user to retake it, right? So especially in a mobile scenario where you have control over the capturing process, this is very easy to do. This would just be a component of the face recognition sample. So we just reject the poor quality sample and say, this is not good enough for reliable matching, so let's take another one and try to make it of better quality. And again, if we talk about quality, right, I discussed some points how general purpose image quality is defined, but face image quality is something else. So there's an ISO standard that defines quality, and it has three different aspects of what face image quality is. So the first one is character. That's not really that much related to the image as it is to the sample itself. For example, if I capture a face image, the person may have a scar, maybe, I don't know, a deformation somewhere, or a very odd thing, I don't know, an accessory, a permanent accessory or something like that, that would impact, right, a face recognition system. So it's not a matter of the image being bad, but the sample is something that face recognition models usually don't perform well with, right? So that's character, textures, scars, the deformations, things like that. Then another aspect that the standard defines is fidelity. So fidelity means the similarity with some source face, right? This is meant for applications like super resolution or denoising or something like that, where you have a reference and then you can say something about the fidelity compared to the reference, right, of your restored image. And the third one, which is actually also the most important these days, it's called utility, right? This says something about the fitness of a sample for face recognition. So it basically says how useful is this face image for face recognition model. So we are not talking about quality from the perspective of humans, right? But we are talking about quality from the perspective of a face recognition model. So if I look through the eyes of a face recognition model, is this a good image or is that a bad image, right? And typically images that produce unreliable scores are considered bad quality samples. For example, if I have a profile image, something like that, this is, even if the resolution is perfect, this is considered bad quality because face recognition models expect frontal images, or let's say, in other words, they work better with frontal images, right? So utility or the usefulness of the sample for face recognition is how quality is now generally defined for. So this is how we would these days treat face image quality. And I have a few examples just to show you what I mean, right? And that you see that there's a difference between perceptual quality, what humans perceive, and face image quality, what face recognition models perceive as high quality. So this image, for example, if I would ask you, right, the audience, is this of high quality? Probably the majority of you would say yes. So we have a frontal image, it's high resolution, there's no blur, very little noise, and for humans, this would be of high quality. But also for face recognition models, right? Again, we have a frontal face, a neutral facial expression, The background is homogeneous. It's high resolution. So face recognition models would consider that a high quality sample. Now, if you look at the second example, so here, still, if I ask humans, they would say this is a high quality image, right? Again, it's very sharp, it's crisp, no noise, and so on. But for a face recognition model, this is a low quality face. Why? Because it's occluded, right? So the occlusion is not something face recognition models would like to see, because half of the information they use for recognition is missing. So this is generally considered a low quality face image for face recognition models. And then you have the other spectrum where, for example, this image, it has a lot of noise. It's a profile face, side profile face, and so on. So humans would usually rate this one as low quality, but it would also be a low quality for face recognition models. So you can see general image quality and face image quality, it's not the same. It can be in certain situations, but in general, it's not the same. So what we want to do when we build face image quality assessment models, we basically predict a score, right? And this score should be higher for good quality samples, and it should be lower for low quality samples. And we call this a unified quality score. Now, why is it called a unified quality score? Because we are not able to say where this score comes from, right? It's a mixture of different components. So it considers the illumination, the frontalness, the pose, the expression, and so on. But all of those factors are compressed into one number. This is different from, let's say, what we call quality components, and also the standard defines quality components, right? If you want to build a face recognition system and have all these quality measures incorporated, the ISO standard also defines different components. So for example, facial alignment, so is where are the landmarks, right, compared to where they should be? Is the background uniform? Is the image sharp? Is the mouth closed? Are the eyes open? How frontal is the face? Is there any occlusion? And so on, right? All of those are components of quality. And you can develop a method that would estimate each of those as a sort of additional score or one score. But typically, this unified quality score encapsulates all of those in a certain manner. But it's just not transparent, right? So we don't know what is going on behind the scene. So we usually think more of this quality estimator as a black box that gives you a quality score that you can then use for rejecting samples, or maybe for as a regularizer for your face recognition model or something like that. And if you look at what approaches are out there, so there's different groups of face quality estimation models. How we divide those is into analytical. So what analytical models do is they just compute the score directly from the image sample. So and this can be, for example, sharpness, level of occlusion, frontalness. So you don't need anything else than just the image to get the score. And also you can estimate the unified quality score. And here's an example. So these methods in general are easy to implement. They are computationally very simple, but on the downside, they don't really produce competitive scores from today's perspective. And here's an example from 5 years ago or 6 years ago from Philip, one of our colleagues that we collaborate with also regularly. So what I did is they tried to estimate what happens if you generate a template from a face image and then have sort of a dropout layer somewhere, right? If I drop out certain components, the template should change just a bit, right? So if the representation is stable, if I drop some components in the model, this should not change a lot. So what I did is they used a ton of, let's say, these dropout components to compute different templates, and then they compared different templates among each other. And just to get you in intuition, if this is a stable image, a good quality image, a comparison between these should give you a very high similarity scores. And you can translate that into high quality scores, right? If the template changes a lot because you just dropped a few units in your neural network, then it's probably not a good representation, and because the image is not stable, right? And that would give you low similarity between these components or these versions of the templates, and consequently a low quality score. And this was one of the first methods that really pushed what face image quality assessment can do. And it's still very popular today as a baseline when you develop novel techniques. Then the second group of approaches, which I would say is probably among the most popular, it's regression based. So what that means is that, for example, you have a data set of images of different quality. The quality is somehow labeled, and then you simply build a regressor that estimates these labeled scores from the input image. And this sounds very simple, right? And the process itself is simple, but what it boils down to is how you estimate the quality labels, right? These pseudo labels, because you need to have some sort of ground truth. So you shift the problem from how to estimate it into predicting scores that you computed somehow. And here's an example from an earlier work from 2018, where the authors used mean opinion scoring. So they basically asked people to get labels on the images. And from that, they simply used a backbone neural network to get features, and then built a support vector regression approach to estimate these labels that they had, right? And this was also very simple. And if you think about state-of-the-art approaches, you can find some state-of-the-art techniques that still follow this paradigm. So with regression-based models for predicting scores. And the last approach that I would say it's probably the most popular these days is model-based. So what we think about model-based is that you have a face recognition model, and next to the model, next to computing the template, you also derive a quality score somehow, right? And there's, again, different ways how you can do that. And I will talk about different options for model-based approaches very shortly. So before we move to the, let's say, some of our approaches that we developed, maybe some more words about how we measure performance of face image quality assessment methods. So I assume you all are familiar with face recognition and how face recognition works and how performance is measured. So usually what we do in a verification scenario, for example, we would have a database. We would generate a lot of mated comparisons, so that is with images of the same identity, and a lot of non-mated comparisons where you would compare images of different identities. And then for each comparison, you will get a score, and the distribution of the scores would look like that. So if I want to make a decision then in a face recognition system, I would say everything below this decision threshold is the same identity. Everything above the decision threshold is not the same identity, right? And based on this comparison, I can now make decisions about face recognition, right? But of course, some of the scores for this mated comparison fall on the other end of the threshold, and all these scores would contribute to false non-matches. And some of these non-mated comparisons also fall on the wrong side of the threshold, and these would then be false matches, right? The errors that you get in a face recognition system. So if you try to evaluate face image quality, the assumption is that poor quality samples generate false non-matches, right? So if I go back, if one of these images here is of poor quality, the comparison, so the distance would be large, and we will generate a false non-match, right? So that's why we usually evaluate face image quality in this way. So we fix the false match rate at a certain number, and then just observe what happens with the false non-match rate if we reject the poorest quality samples. So on a data set, we would run our quality estimator. We would rank the images based on quality, And for example, if we have the entire data set, we observe that the false non-match rate is maybe 0.03. But if we drop, so we remove 10% of the lowest quality images, we assume now we removed the images that contributed the false non-match rate, this error needs to drop, right? And it drops, like you can see here. And if we remove 20%, it drops further. If we remove 30%, it drops further, and so on, right? So the steeper it drops, the better the performance. So we sometimes measure face image quality with the area under this curve, which we want to be, so we assume it will be very small, and the smaller it is, the better the performance of your quality estimator. So that's the general idea of how you estimate quality in these types of models, right? It's meant for face recognition, so that's the reference for us to see how it behaves if we remove poor quality samples. Okay, and this brings us now to the more interesting stuff, which is actual methods, right? And the first method I would like to talk about is FaceQAN. So FaceQAN was presented at ICPR a few years ago. The source code is publicly available, also the paper if you want to read it. And the idea here is we were asking ourselves the question, so how difficult is it to perturb an embedding of a facial image? For example, if you have a face image, a face recognition model, the usual approach would be, okay, I have this image, and then I generate a template, right? And what happens if I try to perturb this template, right? So I can try to run an adversarial attack, see what happens with the input image. So we get some noise, some adversarial noise, and then I can check what happened with the template, right? So the template would, of course, change. But now, our assumption was that if I have a good quality image, then it's very difficult to perturb it, right? So I need to add a lot of noise to be able to shift the identity of the face through another identity. And if I have something that's low quality, like you see here, then if I need to add adversarial noise to change the identity, I don't need much noise because the identity signal is already very, very weak in this image. And it turns out that this is actually true. So if you generate an adversarial attack on high quality images, just a very, let's say, superficial inspection shows you that the amplitude of this noise is 40 times larger than the amplitude of this noise over here for the low quality samples, right? Now, what I'm showing is two extremes, right? Really good images and really bad images. But quality is a spectrum. So it's not as easy as just looking at the amplitude, right? You need to do a bit more. And I will show you, based on this idea, right, that we can exploit how stable the embeddings are for face quality estimation. I will show you how we built a face quality estimator that performed very, very well from this concept that's here presented. So here's the illustration of the approach, and I will let's say it looks complex, but I will talk you through. So the key components of this is that we are operating in the embedding space of the face recognition model. So we are not looking at images, because that would be perceptual, right, like humans do. But we are looking in the embedding space, what happens with the templates, with the embeddings. So this captures this aspect that I was talking about before. So we are looking through the eyes of a face recognition model. What we do is we first initialize from the initial image, we add some noise just to displace it, right? So in the embedding space, we are not in the same point, so we displaced it a bit. And from here, we are starting template-based adversarial attack. So concretely in our approach, we use the fast gradient sign methods with some basic iterative method to get an adversarial attack like that. You see, and we run that for a fixed number of iterations. Now, this will already give you an adversarial approach where you can measure the similarity of these two in the embedding space. But what this does not capture is pose changes, right? So if the pose is something that's profile, a simple adversarial attack will not capture that. So because of that, we used an additional operation where we just flipped the image. So instead of having one image, we also flipped it. And you can imagine if this is very frontal, then the flip operation will not do much, as you can see here. But if this is a profile face and then I flip it, it will look the other way. So this will be somewhere completely different in the embedding space, right? It will be over here, not very close. And that is the point where we model pose. And we repeat this process k times because, as you know, adversarial attacks are somehow stochastic, right? And just to average over this randomness, we repeat this process several times. Now, once we have all these images generated, we can use an aggregation function to compute the quality score. And what this does, it's quite simple. So first, we compute the similarity between this original embedding and the embedding of the adversarial attack. And as I said, we did this k times, so this is k different scores that we get from here. And the score here is simple, just cosine similarity. And then we also compute the cosine similarity between the flipped face and the original face. And as I said, if all these images are stable and of high quality, these similarities should be very high, so close to 1. So we can compute the average and also take the standard deviation into consideration. And finally, just combine it with this flipped image in a single score that gives you the quality estimate. So this is all given to a power of p, but this p just takes care of the range of the quality scores so that they are within a reasonable range, right? It doesn't have any other function than that. So we evaluated this approach with standard error versus discard characteristic curves. So those are the curves that we talked about before. We measured the AUC, so lower scores mean better results, on 4 different benchmarks. Then what's important, because we are looking for the quality through the eyes of a face recognition model, right? It's important that we test this with different models because they can behave differently. And also in this specific case, because we are studying the adversarial attack, we have a same model and cross-model scenario where same model would mean that we are running the adversarial attack on the same model that we are testing on for quality estimation. And cross-model would mean that we are producing the adversarial attacks offline and they are running on a completely different face recognition model. And we are comparing to 7 different face quality estimation models. And you can see the results over here. The thick green and thick red curve are the ones that we, for FaceQAN, one is cross-model, the other is same model. And you can see that for the majority of data sets, we achieved state-of-the-art results at that point. So we are always the lowest or among the lowest. And it's also very interesting to see that it doesn't really matter if we are on the same model or on a different model. In both cases, the curves are very, very similar, right? So which shows that this generalizes well across models, and the adversarial attacks also generalize well to different types of models. Here's an example of how we can order a data set based on these quality scores. Right, you can see that the ordering is different for different models, but in general, you can see the big picture, right? Frontal faces receive the highest quality, and then you have blurry and side faces with lower quality. And what's interesting, for example, in this case, an image that's blurry but more frontal would get a higher score than an image that's not blurry, maybe has a cap that includes parts of the face, some sort of facial expression, and maybe a bit stronger pose, right? But in general, you get a decent ordering. Now, on the downside, we also evaluated the speed with which the model performs. And you can see, because adversarial attacks are very slow, in terms of speed, we are not competitive. So other models would need around 4 milliseconds to produce a similarity score, quality score. With us, the fastest, it needs 200 milliseconds, right? So much, much slower. But the results are therefore better. So if you have time, if you can afford the computational complexity, this approach is pretty competitive, but it's comparably slow. So yeah, this speed was one of the biggest issues with these adversarial attacks that we use for face quality estimation. And because of that, we tried to develop another approach based on diffusion, which is called eDiffIQA. And this eDiffIQA was initially presented at IJCB in 2023. And later on, we extended this to an extended version of DifFIQA, so eDiffIQA. And this one was published at the IEEE Transactions on Biometrics, Behavior and Identity in 2024. Again, the code is available, also the paper, if you want to look at it. Now, if I'm talking about quality assessment with diffusion, so there's two concepts that we are trying to exploit here. One is perturbation robustness, which is similar to what we had with these adversarial attacks, and the other one is reconstruction quality. And I will show you what I mean with that. So for perturbation robustness, for example, you have an input image, a face recognition model that produces an embedding. If I now change the quality of this image a bit, for example, I can add noise to it, then I will get another embedding. And of course, if the image is high quality, this noise will not impact the template a lot. So these two will be very similar, right? And for example, if I have a bad quality image, I compute the template and then I add additional noise to it. Now the image was already very bad. So this template here was not really stable. Because of the noise, I will now get something completely different in the embedding space, right? This will be somewhere else in the space. And if I measure the similarity here, it will be very low, right? The distance will be large and the similarity will be low. And then there's another approach, right? If we think about noise, that this was just noise, I can simply train a restoration model to restore the original image back, right? In this case, I would use a denoising model, for example. And because this denoising model is trained to produce good quality images, this template from the restored image would again be very similar to these ones. But if I apply the same restoration models on this blurred, bad quality image, even the restoration model will not be able to restore it, right? If I push this through another face recognition model, I would get an embedding that would again not be the same as the first one, and again very similar. So if I just measure the distance between these, it will be large, right? And you see these two concepts I can encapsulate into a diffusion process. This would be forward diffusion, and the other one would be backward diffusion, right? And this is how we built another technique. So it's very simple. In the first step, we use forward diffusion to add noise. And in the second step, we restore it. And based on that, we can then estimate quality. And now let me show you how this works. Again, we use the same trick, right? Because all of this does not model pose. So we just flip the image first. You can see if it's a side profile image, you will get another profile. So the distance between these will be big. We then noise them, denoise them, and this gives you 6 images for each input, right? And if I want to use estimate the quality score, again, we said we need to look through the eyes of a face recognition model. So for these 6, we would compute the embeddings, and then simply all possible similarity scores between the 6. So cosine similarities, and then we simply average over those. And that's a very simple process, right? We model pose, use the noising, denoising, and then measure similarity between these images in the embedding space and take the average. And that's our quality score. And now I was talking about adversarial attacks being slow, right? But diffusion is even slower, right? So you all know that diffusion is very, very slow. So this is still a problem that persisted. What we did here then to speed things up is we use knowledge distillation, right? I can take a data set like VGG phase 2, which has millions of images. use our DifFIQA approach to get quality labels, and then simply train a regressor, very simple cause-phase backbone with a layer to predict the score. And then we just distill this information into this feed-forward network, right? And this then gives you a straightforward. So you just need a single pass through the model to estimate quality. And ideally, it should work the same as this DifFIQA approach based on diffusion, right? Just don't be as slow as that one. Again, we did even more experiments than with FaceQAN. So you looked at partial area under the curve scores, for example, up to 0.2. You know, you are not really interested when you measure quality. What happens if you reject 90% of your data set? Then it doesn't make sense, right? You want to be very good at after rejecting maybe 5%, 10%, up to 20% of your samples. So that's why we are looking at the area under the curve up till 0.2 or up till 0.3. So again, these experiments were over 6 or 7 data sets, 4 face recognition models, and in comparison to a lot of baselines. So just to give you the gist of it, it turns out that the regressed version and the diffusion-based approach, both of them produce state-of-the-art results, right, compared to anything else. And what is interesting, if you look at the original diffusion approach, which needed 1 second to estimate the quality score, the regressed, the distilled approach needs just 1 millisecond. So it's 1,000 times faster and still state-of-the-art, right? So it's very, very, very fast. So here's again some examples of how the distilled and original version look like. They produce similar quality scores and are very similar rankings. So basically they are the same, which means you are able to distill all this diffusion stuff into a feed-forward network without the computational complexity. Now, maybe what to take away from this approach is that it's available in OpenCV. So if you want to use something, it's part of the model zoo of OpenCV now. And we also submitted this to a NIST challenge. So NIST is ranking different algorithms for face recognition, and part of that is also quality estimation. And this eDiffIQA approach, it ranked first in the kiosk test, so kiosk quality data. And this one is the last one that I wanted to talk about today. So the last approach is called FROQ, and it was published at IGCB last year in 2025. And the idea here is, if you look at supervised face image quality methods, right, those that need labels, you need to annotate them somehow or estimate them somehow. The training is complex, and usually those are model specific, right? So if you have a different face recognition approach, you usually need to retrain them to be optimal in performance. But once they are trained, they're very efficient at runtime. But unsupervised techniques, on the other end, they usually don't need training at all, therefore perform less well and are slow, but they are very easily adapted to arbitrary models, right? So if you have a face recognition model, you can every time use an unsupervised technique, and it will work more or less the same as with other models, right? So there's an upside to both of these approaches. So what we wanted to do with FROQ, which is a semi-supervised approach, is find a trade-off between the two. So something that's efficient, that does need training, and that still provides competitive performance. Now, what FROQ stands for is observing face recognition models for efficient quality assessment. That means we are looking at the information that's already in the face recognition model, and from that, we are just computing some quality score. And there are some main components, right, to this approach. We have a face recognition model, which can be anything. We have something that's called a quality observer. So that's the main module that computes quality. And this observer needs to be initialized before you can use it for quality estimation. And how that works is, all it does, it's computing feature norms of intermediate layer representation. So when you give a face recognition image, a face image to a face recognition model, within the intermediate layers, you will get some representation, right? And we can use the norm of those representations as sort of quality indicators. So how we do that, we still need to initialize it, right? That's not really training. It's just some sort of, let's pick the best layers to have for norm computation. We take a small data set of face images. We use auxiliary FIQA approach. So for example, any of these that I discussed could be used, but we use something very similar, simple here. This gives you pseudo labels that you have in these listed here. And finally, we just find the best layers in such a way that if we compute on the L intermediate layer, the norm, that the correlation between these scores and the quality estimates of the norm is the highest, right? And in this way, we can find B layers that we can use for quality estimation. So during runtime, we just compute the norms for all these layers, sum them up, and that's our quality score. So very simple. And if you look just what this gives you, right, the approach, the technical approach, we do require quality labels similar to many other approaches, but we don't need any specific architecture. So this can be applied to any face recognition model, and actually without additional training. We just need to identify which layers to use, which is sort of an initialization, and that's it, right? We don't need any custom losses, any optimization on the network, or any separate neural network, right, predictor. None of that is needed. So we can compute quality with a single pass through the face recognition model. So you compute the template anyway, and if you just compute the norms and sum them up, this gives you also the quality estimation. No backwards passes are needed. And all of that is happening at the representation level, right? So we are just looking at the representations that are produced within the face recognition model. So again, we used a very similar approach to evaluation, and you can see that if you compare results, so we are not the best, and we are not claiming to be the best, but we outperform all unsupervised methods. And compared to the supervised methods, we are among the top 3, for example. And if you look at the speed, right, also compared to the unsupervised methods that are, let's say, readily applicable to any face recognition models, we are much, much faster. So really, really fast. So comparable to what supervised methods do. But supervised methods, as I said, if you want to have the optimal performance, you usually need to fine-tune them on the given face recognition model. So they are sort of face model specific. FROQ is relatively stable compared to the model selection. So we also did a lot of experiments with face image quality for face recognition. So not to reject samples, but to improve performance. And I just have one slide on this, and then I'll move to the open challenges for my closing. So we recently proposed FunFace. So this was published at FG this year, so at Face a Gesture, where we incorporated biometric utility into the face recognition model. And as you can see on very challenging data sets like DroneSurf or SurfFace, which have very bad quality data, we were able to outperform like methods or models that are considered state-of-the-art today, like AlphaFace, ElasticFace, or MacFace, and by a large margin, that is. And another approach that we just published a couple of weeks ago, there we incorporated quality into video-based face recognition. And also here we were able to outperform competing techniques like AraFace, ElasticFace, or MacFace by a considerable margin for video-based face recognition problems. Okay, that was more or less a general overview of what is happening in face recognition and how face image quality can help with that. And I would just like to conclude with a few open challenges just to show you what needs to be done or where the open issues are. So face image quality assessment can still be better. It can be faster. It can require less resources. And also the fairness here is still a problem, right? It can be a problem. So does it really work the same for different demographic groups? What is really open, and I guess it's needed, is estimating the quality for synthetic data, right? You can use general purpose image quality assessment methods, or even some of these FIQA methods to estimate the quality of generated data, but that still doesn't give you an estimate of how good this data will be for example, training face recognition models. So there's probably something else that we need to consider, and that would be important to develop, right? We don't have something like that yet. Then all these approaches are still sort of sensitive to the specific pipeline that you use. For example, a face recognition pipeline would have a detector, a landmarking approach, and then a model that extracts the template. And the variability there would always impact face image quality assessment somehow. So if your detector doesn't give you precise or consistent bounding boxes, that would, of course, impact how your face quality estimation model would work. So improving robustness to these things is really important. Another one is if you have really low quality video, right? So in videos, you have a lot of frames, and all the frames are of very similar quality. So finding something that can distinguish the quality of one frame from another and say this one is better than the rest would really be important, especially for applications that require processing these low quality videos, right? And I think that video-based FIQA is very different from still images, and not a lot of work has gone into that. And what I think is also critical, for example, we are these days estimating unified quality scores. So one number from the image, but some vector descriptions would also be important. For example, sometimes you're not just interested in what the quality of an image is, but you want to match similar quality images, right? For example, for some retrieval applications, maybe I'm interested in a certain quality of a frame that I want to look at. And in these applications, it may be more important or important to have a vector description, so a feature vector, an embedding that just estimates quality, nothing else, not identity, right? So, because sometimes it's the performance of face recognition models degrades because of mismatches in quality, not because one image is bad, right? But because the other one is not the same. And sometimes you want to compensate for that, right? So estimating vector quality would be very important in the future. So this is all that I had for the talk. So I hope you learned something new. And if you have any questions, so I'm very open to answering them. And I also need to thank my colleagues, Žiga Babnik. So he's one of my PhD students who did all of this work on quality, and Peter Per, who's also one of my colleagues, helping to supervise our students. All the publications, if you're interested, you can look them up through the QR code on the left. And all the code is also public, so if you want to reproduce any of that, you have the code on the right. So thank you very much.
Thank you, Professor Štruc, for your excellent presentation. And now we'll move on to the QA session. And there are many questions in the QA window, and I will choose some of that. The first question is from Aman Verma. Maybe this pronunciation. He or her question is about the 3 characteristics. I remembered it as character, fidelity, and utility. And he or she wants to know that are these 3 characteristics independent of each other?
Yeah, so they are usually, I would say, not independent, right? So these days we are trying to estimate utility, which is also the most useful if your application is to reject samples. Then you don't want to have samples that are of bad quality going into the face recognition model because your decision would be unreliable. But then other types of quality, right? For example, fidelity. In this scenario, it doesn't apply. So fidelity usually needs a reference image, and you don't have that. So when we are talking about utility and this unified quality scores, it's meant to be blind quality estimation or no reference quality estimation. And fidelity would be more for applications that have a reference. So it's a completely different use case. As for character is probably, let's say, related to both fidelity and utility, because if there's scars on a person's face or some sort of marks, those probably impact utility to a certain extent, depending on how large the area is, right? But in general, at least character would be related to utility. But you can think of different applications and different quality estimators that would use different aspects of the standard, right? But just for face recognition, it's mostly utility these days.
Okay, the next question is about the quality labels. Alan Nor want to know that whether the quality labels would be subjective or objective.
Yeah. So the first methods, so if you go back 6, 7, 8, 9 years, they were mostly subjective. So the studies were based on asking people for their opinion on the scores. And then they would build regressors that would predict those kinds of labels. These days, it's not like that anymore. These days, you would produce probably some matching scores, and based on the distribution of these scores, you would estimate some label. So you could estimate where it falls, right, compared to the threshold, and this could already be a quality estimate. So how far away you are from the score, for example, or from the threshold. So there's different strategies, and a lot of them on how you can produce the labels. So a lot of techniques also use existing face quality estimation models and then try to correct those labels in a certain way, right, in a smart way, or incorporate additional information, whatever it can be, to fix or to alter the pseudo labels that you get to get better performance. A lot of different strategies can be used here.
Okay. The next question is also from Aman Worma. He wants to know about the quality scores, the normalization. He or she want to know, are the quality scores normalized? If yes, what's the normalization factor?
Yeah. So it depends. So probably we need to talk about academic work where people don't really care that much about normalization. And then you have the ISO standard, which assumes quality scores on a scale from 0 to 100, right? Where 100 would be the best and 0 would be the worst. But that's relatively easy to do because you can use a calibration approach or some function that always produces a mapping to this interval, right? So I would say that for interoperability reasons, if you want to have this applied to some industrial application, you probably need to normalize it between 0 and 100. Otherwise, for academic studies, that's not that critical, right? We are more interested in what the impact of the score is on performance, or how good does it perform, right? Not that much on the scale. So it depends on your work area, I would say.
Okay. And the next question is from Ming Yang. He or she states that a unified quality score compresses factors like pose, occlusion, and illumination into one number. He or she wants to know, do we need more interpretable component level quality assessment in the future?
Yeah. So how the field developed, it went the other way, right? So we had all of these components before. So if I think back 20 years when we were doing face recognition, so quality was basically defined through these components. And then it's more of a heuristic how people use that. So someone would maybe filter images based on illumination, based on post, and build separate models for each component and so on. And that's how it was done in the past. Now, a lot of industrial models, so something that's deployed in practice somewhere, still use some of these, right? Maybe for quality checks, maybe for some internal processing so that they fork into some other pipeline and so on. And all of these are still valid, right? The unified quality score just computes one single number that would tell you how usable this sample is for the face recognition model. That does not mean that other components are not useful, right? In my implementation, for example, I could still use something else. So that's not a problem. But it's interesting to mention there was a study a few years back where I think it was a company that had all these quality components and also very good algorithms for estimating all of these components. And they were trying to build sort of a weighted combination of these components to estimate this unified score. And it didn't work that well, right? So they got a score. It did perform to some extent, but it was not competitive to these state-of-the-art methods like the ones that I presented today, right? So that means there's more to quality that people can hand design, right? It's similar to how we did feature engineering in the past, right? So we did all these handcrafted features with all these descriptors, and now we have CNNs, so deep learning models that learn representations end to end. So we are basically avoiding this manual cycle of designing things and then always missing some parts of what is important, right? So I think from where we are now, this works well, but maybe in the future, if there's some need for some interpretable components, you can do that as well.
Okay. The next question is from Sunda Alma. He or she wants to know about the ground truth. Is there any public data sets labeled with quality class?
Yeah, so there's no such ground truth, right? Because also when we try to evaluate how good these quality estimators are, we are doing this through a proxy, right? Through a face recognition model. So having a reference label is, yeah, it's not that critical from that perspective. But then there's of course data sets that have these labels. For example, I don't remember the name of the data set, but for human perceptual quality, there's a lot of data sets, also relatively large ones that you can use, but that would be human perceptual quality. It's not face image quality as I was talking about today. It's similar, more similar to image quality assessment applied to faces, right? Where you would ask humans to rate things, and then you could build a model on that. There was a PAMI publication a couple of years ago on that. For face image quality assessment, I'm not aware of ground truth labels, right? Because that would be the gold standard that would produce for a face recognition model the optimal curve, right? But then again, all these measures are model specific. So you cannot have ground truth labels because they change from ARA face to ARC face to COS face, right? They're different for every model. So the short answer would be no for face image quality assessment and yes for these perceptual quality assessment tasks.
Okay. Another question from Emma Verma. It's about large language models, which is really popular in recent years. And he or she wants to know that is there any approach exploring using LLM as a daughter?
Yeah, so there are approaches that use text, for example. So one of the early, I think it's called ClipFIQA, uses clip to align text embeddings with face image quality, and that's also very competitive. So for actual LLMs or VLMs, I'm not sure, but I'm pretty confident there are methods, right? So we didn't work with LLMs for this task so far, but that's definitely something we plan to explore in the future, right? Just because of the popularity of it. And it gives you another aspect, right? So this interpretability that I think one of the people in the audience asked before. So if you have an LLM or VLM, you can also get other information from the image, not just a unified quality score, right? Maybe also these components. And you could probably design it in a way to give you more information than just one number from using the VLM.
Mhm. Okay, the next question is about your method FROQA. And he or she wants to know if the face recognition needs to be trained over a large scale face data set so that the embeddings are not conditioned on the training identities.
Oh, so this FROQ approach is very, the main idea of that was so it's independent of the face recognition model, right? So you need to think about face image quality assessment as an add-on component of face recognition model. So even if it's deployed, if it's running somewhere, you don't have access to the model or the training code for the model, you can use FROQ to estimate quality from that. So that was the main idea. We didn't really train the face recognition models from that. We took some pre-trained models and then showed that it's applicable to all of them. And with all of them, it works pretty well. But in general, of course, right, if you need to train a face recognition model, you need a large data set. And then the training data for FROQ is not there because we are not training it at all. So we are just looking for the best layers to use. And that's all we do, right? So our approach doesn't have any hyperparameter beyond the selection of the layers. That's all there is. So that's why it's so, let's say, desirable, because it doesn't need training. It doesn't need any optimization. It's just looking at the norms of certain layers and then summing them up. So it's very, very simple and efficient.
Okay, the next question is about the standard, the quality standard. Do you have any comments on the recently published face quality standard and its reference implementation? Have you conducted any evaluation or comparative analysis against it?
Yeah, so this open source implementation, or FIQA, that's used, that's in the standard, right? So it has MUC defined as the reference implementation. And if I would go back to my slides, so we are actually comparing to MUC every time. And MUC in this public evaluation is not really competitive at all. So maybe another point that I need to explain, where performance is usually measured also by NIST, for example. In academic papers, you would see a lot of times that the reject rate is set at 0.2, so at 20%, or maybe 0.3 at 30%. But then NIST measures this at 2%. So it's very, very close. You just reject 2% of the images. And in that area, these models, they are not optimized for that. And they always perform sort of suboptimally. And in that setting, this OFICA performs best, right? But I would say it's sort of optimized for that operating point, but in general, it doesn't give you competitive results. So that, at least that's my experience. So there may be people that have another experience with OFICA, but for us, it was like that. And if you look at the papers, it's also that setting is reflected across the field, I would say.
Okay, we will have two questions more. This question is about what will be most challenging task if we assume all the images are of high quality?
Yeah, I mean, there's probably a threshold on the quality that face recognition in models can process. And if it's all high quality, right, that's not really a big problem for face recognition models. Because I would say probably the other end of the spectrum is more problematic. People these days, they use, because of this Gen AI and all these capabilities of restoration techniques, they try to restore very poor quality images to something that's higher quality, and that's already not a good idea, right? So doing any restoration for face recognition, I would not recommend it. And on that end, we simply need to say below a certain quality, it doesn't make sense, right? And this is where face image quality assessment techniques come into play. If we still think about face recognition as the application, the higher quality images, they are not that critical, right? If I get the score of 95 or 100 for some image, it's not really important. But maybe somewhere else, right? If this would be perceptual quality for some, I don't know, marketing application where I would use a face image, maybe in that sense, it's more important, right? If I can distinguish the quality of high quality images better, but for this certain application, it's not that critical. But it's a good question. Yeah.
Yes, very interesting. Okay, the last question. With the regulations demanding auditability and explainability for AI-based systems, how has model-based quality assessment changed? And how does handcrafted methods compare to these models in relation to usability and explainability?
Yeah, so that's a very good question, right? So in Europe, we have GDPR, and GDPR requires transparency, but that usually is defined in a certain way that AI assistants need to be explainable if they impact humans, right? So that means for face recognition system, where the decision may have an impact on someone's lives, that needs to be explainable. But a face quality estimation network, which does some pre-processing for the face recognition system, it's maybe not that critical, right? If it's not explainable. So we are doing a lot of work on face image explainability or face recognition model explainability. And I could have another webinar on that topic, right? How to look into what's happening in the face recognition models, what happens with the decisions, right? What's the basis for the decision, and so on. And I think that's the more critical part of this auditability and transparency aspect. For face image quality, I would say it's not that big of an issue because even considering these regulations, it doesn't have that big of an impact on humans, right? Because it's just rejecting images at the front of a face recognition model. Yeah, in short, right? But of course, if you have all these components, you can say something also with respect to the face recognition model, what happened, right? Why did it give a result that it gave?
Okay, here's another question, and yes, that's the question I want to answer too. So I'll add one question more. Um, Viewers, you want to ask whether face image quality assessment methods have general applicability to quality assessment for other biometric modalities.
Yeah, very good question. So it depends on the modality. So there are certain modalities where you could just take one of these face image quality assessment models and apply it almost out of the box on another modality. For example, this FROQ, this is universal. As long as you have a modality that's processed by a CNN and then outputs a template, you could use FROQ for estimating, I don't know, periocular image quality, iris image quality, or something else, right? But it's not the same as, for example, in fingerprints. Fingerprints usually try to extract minutia, and it's not a CNN that you use for that, like input image CNN template, right? In those kinds of modalities, you would probably need to change the approach a bit. But as long as it is conceptually similar, it would be just a matter of retraining on new data, and then you would get quality estimators that would work, in my opinion, reasonably well for those modalities as well.
In your opinion, is there any limitation of the methods we discussed today?
Yeah, so limitations in terms of, there's of course open problems, right, which I try to discuss a bit. In terms of limitations, it's always the issue, right? If you have a deployed solution somewhere, efficiency is a big problem, right? So if you have something heavy, like I was talking about eDiffIQA, which needed a second to produce an output, and then if you are on an edge device, that may not be feasible, right? So efficiency, I would say, is definitely something that people need to look at when they do face image quality assessment for deployed systems, right? Yeah, that would be probably the first thing that comes to mind.
Okay. Now, once again, thank you, Professor Štruc, for joining us for this webinar. And this will be the end of this webinar. And I will make some advertise that our next webinar is scheduled for the last week of July. So for all the audience, please keep an eye on our website for updates. We look forward to seeing you next time. And goodbye, everyone.
Thank you. Goodbye.
Goodbye.